The Importance of Lifetime Learning. Pattern Recognition and Viscoplastopology, number 1483, VPT Sharp 044, December 29, 2025. Gerald C. EclaireMD Foundation. Category: Learning, Pattern Recognition, Research Methodology. Preface: My grandson will graduate next May from Princeton University with undergraduate degrees in applied mathematics and artificial intelligence. Recently, I had a long and meaningful conversation with him about what truly matters in building a strong and durable intellectual foundation. I explained to him the importance of having a solid foundation in life, philosophy, mathematics, and physics, because they guide values, logic, and understanding of the physical world. I also pointed out that his preparation in physics was not yet sufficient, and would need further strengthening. I even used strong words, stating that everything we can observe in this world must obey the basic laws of physics. In other words, if something can be seen, measured, or detected by human beings or instruments, it cannot and will not violate basic physical laws. Present physics may not yet fully explain everything we observe, but nothing we observe lies outside physics. What remains unexplained today is not beyond physics itself, but beyond our current understanding or measurement resolution. These foundational disciplines train the mind to think from first principles. First principles mean thinking logically and trusting one's own reasoning, building understanding from the ground up using logic, instincts, and basic truths, rather than relying on habits, averages, mainstream positions, authority, or what others say. They help a person understand systems, structure, constraints, and causality, and to reason clearly when facing unfamiliar or complex problems. I also told him that holding degrees is far less important than possessing real knowledge. Shining degrees may bring self-pride and social prestige, but solid knowledge brings true strength, both in improving oneself and in influencing others. Knowledge determines how a person thinks, adapts, and solves problems when conditions change, or when standard tools no longer apply. I further emphasize that learning does not stop when one earns a doctoral degree or any formal credential. In reality, serious learning often begins only after formal education ends, when curiosity, discipline, and responsibility become self-directed rather than guided by syllabi, exams, degrees, or institutional expectations. This is the true meaning of lifetime learning. I fully believe in what I shared with him. These views reflect lessons learned from my 6 decades of nonstop study and self-learning, professional work across multiple fields, entrepreneurship, and personal experience through many ups and downs in my life journey. A strong foundation in mathematics and physics, combined with lifelong learning across 8 different academic disciplines, provides resilience that no single degree or fancy title can guarantee. That conversation prompted me to write this article. I realized that these ideas may be useful not only for him, but also for many young people who are preparing themselves before entering their professional careers. My hope is that this paper helps readers appreciate the long-term value of deep knowledge, cross-disciplinary training and thinking, and continuous learning over short-term credentials and external prestige. Real strength always comes from within, not from nameplates, external recognition, or outward glory. Introduction. Modern scientific research, particularly in medicine and certain data-driven disciplines such as economics, remains dominated by statistical thinking. One of the most persistent manifestations of this mindset is the debate over n equals 1, n is 1, myself, versus n equals many, n is m, many patients, in medical research. This debate is often treated as a foundational methodological issue, where individual cases are considered isolated and weak, while population studies are considered rigorous and authoritative. Medical school curricula do not require strong training in mathematics or physics, but instead emphasize biology and chemistry. Current medical education is designed for practice efficiency, not for first principles understanding. From my perspective, this kind of training design has limited value when examined through the lens of vector path theory. In simple terms, vector path theory shows that health over a lifetime, learning, careers, or complex systems do not fail because of a single number. They fail because their trajectory slowly drifts in a harmful direction, or suddenly changes course due to an extreme spike. Vector path theory helps us see where something is heading before it breaks, not after. Viscoplastic medicine theory, the VMT model, or the broader framework that integrates geometric topological data analysis, the TDA model, together form what I now call the VPT model, Viscoplastopology. The distinction between n equals 1 and n equals many originates from statistics, not from physics, energy, or geometry. It reflects how statisticians manage noise and uncertainty, not how real systems accumulate damage, deform over time, or ultimately fail. This paper explains why sample size is not a governing variable in energy-based or geometric-based analysis, why pattern recognition depends on structure rather than averages, and how viscoplastopology provides a unified framework for understanding complex systems across biology, history, society, engineering, psychology and medical health. The statistical origin of the n=1 debate. Statistics was developed to address a specific limitation. When underlying mechanisms are unknown or too complex to model directly, statistical methods estimate behavior by averaging across many observations. Larger sample sizes reduce noise and increase confidence in population-level conclusions. Within this framework, n=1 is considered unreliable because it cannot suppress noise. n=many is considered reliable because variability can be averaged out and quantified. However, this logic is conditional. It applies only when statistics is the primary analytical tool, and when mechanism-based modeling is absent. The error arises when this conditional logic is mistaken. For a universal scientific law, sample size is not a physical principle. It is a compensatory tool used when governing equations are unknown or ignored. Energy and geometry do not recognize sample size. From a VPT or VMT perspective, systems are evaluated by stress, strain, trajectory, turning point, energy accumulation, and failure patterns. These quantities are governed by physical laws, not by how many data points are collected. Energy does not behave differently because deformation occurs in one structure, rather than in many similar structures. Geometry does not change, because a dataset is labeled personal or population-based. A stress-strain curve is the same, whether it comes from one beam or 1,000 beams. What matters is whether the underlying physical or biological mechanism is correctly captured. For this reason, the n=1 versus n=many debate is largely irrelevant in energy-based research frameworks. It is a statistical artifact. In firm mathematical geometry and physical energy models, there is no such distinction. Introducing Viscoplastopology. Viscoplastopology is the integration of the following three fundamental ideas. First is viscoplasticity. Systems deform over time. They exhibit both elastic behavior, where deformation is reversible, and plastic behavior, where deformation becomes permanent. What matters are time, rate, and accumulated damage. Whether the data come from many patients or from a single patient does not matter. Second is topology. Topology focuses on geometric shape, form continuity, data points, connectivity, and structural change rather than exact numerical values. It asks how trajectories evolve, where singularities appear, and when qualitative changes occur. Third is vector path theory. System behavior is represented as paths in a multidimensional space, defined by influential stressors and responsive outcomes. These vector paths reveal directionality, curvature, congestion, divergence, and collapse. Viscoplastopology is not abstract mathematics. It is a geometric and physical way of seeing how systems move, accumulate damage, and fail over time. In this framework, the object of study is not isolated measurements, but the evolving shape of the system trajectory. Why sample size is irrelevant in viscoplastopology. Viscoplastopology does not ask how many samples exist. It asks whether the path geometry is coherent, whether energy accumulation is directional, and whether irreversible deformation is occurring. A single well-instrumented system can fully reveal its governing dynamics, if the measurements are longitudinal, dense, and correctly interpreted. Likewise, population data can reveal the same dynamics if aggregated properly. In both cases, the governing laws are the same. During the past 5 years, I have applied viscoplastic medicine theory and viscoplastopology to both personal longitudinal data and large population datasets. In both cases, the same structural patterns appear. Trajectories bend in the same directions. Energy accumulates along the same paths. Failures occur at the same geometric thresholds. If the physics is correct, truth reveals itself, even in a single system, like a single patient's dataset. This demonstrates that the model is mechanism-driven, not sample-size-driven. That is why I do not understand why some medical research scientists argue about the validity and accuracy of n=1 versus n=many. My guess is that, in their research methodology training, they learned only statistics and little else. Pattern recognition as a trained physical skill. Pattern recognition is often described as intuition or talent. From a viscoplastopological perspective, it is neither mystical nor accidental. It is a trained sensitivity to physical behaviors, geometric patterns, system development trajectories, moving deviations, turning points, and failure modes. Pattern recognition improves through specific practices. Longitudinal exposure is essential. Patterns, like a movie, do not exist in a single snapshot, like a still picture. Patterns exist in motion. Observing the same system over long periods reveals stability, drift, acceleration, and rupture. Dimensional reduction reveals structural behavior. Removing irrelevant variables allows dominant stressors and responses to emerge. Geometry becomes visible only after noise is reduced. Shapes, such as curves, areas, and volumes, matter more than single data values. Numbers fluctuate, but shapes persist. Slopes, curvature, clustering, and bifurcation points reveal governing physical laws. Failure cases, such as mortality diseases or structural collapses, are the most informative. Systems reveal their structure most clearly near breakdown. Outliers are not errors, they are early or critical warning signals, similar to mortality diseases in medicine and fatigue, collapse, or rupture in engineering. Cross-domain transfer accelerates learning. Congestion in chips, fatigue in materials, vascular stiffening, organizational collapse, and cognitive overload share the same critical physical and geometric signatures. Feedback closes the loop. Prediction followed by outcome updates the internal model. Pattern recognition becomes reliable only when tested against reality. In conclusion, pattern recognition is the brain learning to see geometry, or human health before statistics, a systems lens forged across decades. This way of thinking does not come from a single discipline. It comes from many years, often decades, of multidisciplinary study and learning, and from sustained exposure to many systems, governed by the same physical laws and constraints. I have spent 43 years of my adult life, starting at age 16, studying 8 academic disciplines at the postgraduate level, including 18 years at 6 universities. In addition, I devoted 9 years to self-study in psychology, reading over 300 psychology and psychotherapy books. I also spent 16 years in intensive self-study of medicine, reading around 10,000 published medical papers. These time spans do not include the many years I worked simply to make a living. For example, I spent 12 years working deeply in semiconductor, integrated circuit chip design using AI algorithms, one of the most complex engineered systems humans have created. That experience helped me, after my stroke in June 2025, understand brain structure more quickly. Because transistors and wires are conceptually similar to neurons and neural pathways, this is not a list of credentials. It represents the intensive and continuous training of my mind. Throughout my entire adult life, these continuous efforts sharpen my pattern recognition capabilities. When stress, strain, flow, congestion, fatigue, and rupture appear again and again across domains, the brain stops switching frameworks and converges on one integrated view. This is the essential spirit of pattern recognition. That is also another view of viscoplastopology. From correlation to mechanism, most medical researchers stop at correlation and regression, but I move directly to disease mechanisms. Most people see categories, but I see energy and geometry. Most people see data values, but I see patterns, including shapes, volumes, trajectories, breaking points, turning points, and possible remedies. This is why my ability of pattern recognition transfers so naturally and quickly across different domains. The domain changes, but the underlying structure does not. Over time and sustained effort, observation and analysis merge into instinctive pattern recognition, often without elaborate computation. The focus shifts from asking, what happened, to asking which governing law produced the outcome. I gradually learned that this level of pattern recognition is rare, even among specialists. It is the product of long exposure to structured data, disciplined simplification of complex systems, and continuous verification across multiple domains. Conclusion: the n=1 versus n=many debate is not a physical truth. It is a statistical artifact arising from methods designed to manage uncertainty. When mechanisms are unknown, viscoplastopology operates on a different foundation. It is based in mathematical theories and seeks governing physical laws through geometry, energy, trajectory, and irreversible deformation. When the same structural patterns appear in both individual and population data, the model is validated as mechanism-driven. Sample size becomes secondary. The completeness and accuracy of the original dataset become far more important than which research method is used to solve the puzzle. Pattern recognition, when trained through longitudinal observation, conceptual clarification and simplification, geometric variation, failure, analysis, and cross-domain transfer, allows truth to emerge. At 79, what I carry is not just knowledge, it is compressed experience. It is the ability to sense trajectory, limits, and failure modes across many systems. This capability was not granted or accidental, it was earned. Disclaimer: I write this article not for fame, but to share what I have learned, so others can understand complex systems, prevent failure, and live better lives. This content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this article freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights belong to the author. Gerald C.